Hello friends, I welcome you in lecture number 2 on Lorentz series. In this lecture we are going to do some more examples on Lorentz series of complex function. So we start with this first example. Write the two Lorentz series expansion in powers of z that represent the function f of z equal to 1 over z times 1 plus z square in certain domains and specify those domains. So here our function is given as f of z equal to 1 divided by z into 1 plus z square, and we are asked to represent this function in terms of Lorentz series with center z equal to 0. So first we keep in mind that our center is nothing but origin z equal to 0 in the complex plane. Now as we know, we can represent our function f of z in terms of Lorentz series if our function is analytic in the annular domain given by r1 less than absolute value of z minus center, which is 0, less than r2. Now here we are asked to represent this function in terms of Lorentz series in certain domains. As we have discussed in the last lecture, that we can have more than one Lorentz series expansion of the same function in different domains. So for that, first we have to decide that our function is analytic at which points, or our function fails to be analytic at which points. So as we know, this function is rational function, so this function is not analytic at those points at which denominator is 0. So this function fails to be analytic at those points for which z into 1 plus z square is 0. So this implies z is 0 and 1 plus z square is 0. That means z square is minus 1, that is I square. So z is plus or minus I. So our function is not analytic at 3 points only, 0, I and minus I. Now if we consider the open disk with center 0 and radius 1, suppose this is this circle with center 0 and radius 1, then because this radius is 1, point I will be here and point minus I will be here. Now function is not analytic at these 3 points, z equal to 0, z equal to I and z equal to minus I. So we will consider the domain in this way. Our function is not analytic on the boundary of the circle at these points I and minus I. So we cannot consider the points on the boundary. So for that we have to consider absolute value of z less than 1, because function is not analytic at z equal to I and minus I. We cannot consider mod z equal to 1. So we are not considering the boundary. Now this point z equal to 0 is inside the open disk. So we cannot consider z equal to 0 also. So to exclude that point, we have to consider absolute value of z as greater than 0. So this is the one domain in which our function is analytic. So this domain is nothing but set of all points inside the open disk except 0. We are not considering origin. So except origin, our function is analytic in this open disk. So this is the first annular domain in which our function is analytic. Here we have considered absolute value of z, that is absolute value of z minus 0. So center is 0 here. Now if we consider the region which is outside this circle mod z equal to 1. So if we consider the region outside this circle mod z equal to 1, then our function is analytic at all the points which are outside this circle mod z equal to 1. So that means we are considering the points for which absolute value of z is greater than 1, and there is no other point in this domain at which function is not analytic. Function is analytic at all the points outside this circle mod z equal to 1. So there is no upper bound here. So here we can write infinity. So this is the another possible domain at which our function is analytic, and there is no other possible annular domain. So here we are asked to find out Lorentz series of this function in certain domains, and we are asked to specify the domains. So as we have discussed, we have these two possible domains in which function is analytic. So now we will find out Lorentz series of function is in these two possible domains. First we consider this domain, and then we will find out Lorentz series in this domain also. So before that we can rewrite that f of z is not analytic at z equal to 0, I minus I only. Okay, so therefore as we have discussed, f of z is analytic in the domains 0 less than absolute value of z less than 1 and 1 less than absolute value of z less than infinity. So requirement of Lorentz series expansion are satisfied. For Lorentz series expansion we require that our function is analytic in annular domain. Here center is 0, so we consider absolute value of z, and for first domain r1 is 0, r2 is 1, for second domain r1 is 1, r2 is infinity. So now we consider Lorentz series expansion in both the domains. First we consider this domain 0 less than absolute value of z less than 1. Now our function is f of z is nothing but 1 by z into 1 plus z square. So we are asked to find out Lorentz series expansion in powers of z. So this 1 by z is already in powers of z, so we keep it as it is. And for this function we are going to use geometric series. We are going to use the Maclaurin series of 1 over 1 minus z, which is nothing but geometric series sigma z raised to n equal to 0 to infinity. So for this Maclaurin series we require that absolute value of z is less than 1. Now here absolute value of z is less than 1, and instead of z we have minus z square. This we can rewrite as 1 minus z square. So if absolute value of z is less than 1, absolute value of minus z square is also less than 1. So we can use this Maclaurin series expansion. So here we write sigma n equal to 0 to infinity. Instead of z we have minus z square raised to n, and the reason is we are considering those z which are in this domain. Therefore absolute value of minus z square, which is equal to absolute value of z square, and which is also less than 1. And we are using the Maclaurin series expansion of 1 over 1 minus z. This is given by sigma n equal to 0 to infinity z raised to n. So this we can rewrite as, if we want to expand this, we can have one more step, sigma n equal to 0 to infinity. This we can rewrite as minus 1 raised to n times z raised to 2n. So this we can write by expanding the summation also. For n equal to 0 we have 1, for n equal to 1 we have minus z square, for n equal to 2 this is going to be positive, and we have z raised to 4. For n equal to 3 we have minus 1 cube, that is negative sign, and this is z raised to 6, and so on. And this is valid in the open disk without 0. And this we can rewrite as 1 by z minus z plus z cube minus z raised to 5, and so on. So therefore our Lorentz series expansion is obtained. 1 over z, 1 plus z square is given by 1 by z minus z plus z cube minus z raised to 5, and so on. And if we wish, we can rewrite this second portion in terms of positive powers of z in this way also, sigma n equal to 0 to infinity. If we consider minus 1 raised to n, then first this term will be positive, so we consider minus 1 raised to n plus 1, and here we have odd powers of z, so we take z raised to 2n plus 1. So this is the Lorentz series expansion of our function 1 over z into 1 plus z square in the domain 0 less than mod z less than 1. So we can observe here this series contains positive powers of z, and we have only one term with negative powers of z. So this series represent the Lorentz series expansion, and in which we have negative powers of z also. Now we consider second domain, which is 1 less than mod z less than infinity. So now we find out Lorentz series expansion for those values of z which are outside the circle mod z equal to 1. So we start with our function f of z is nothing but 1 by z times 1 plus z square. Now here we have absolute value of z is greater than 1. So we have to consider, we can rewrite this as 1 is less than absolute value of z. Therefore absolute value of 1 by z is less than 1, and therefore absolute value of 1 by z square is also less than 1. So if I write z square here, then also it is going to be absolute value of 1 by z square less than 1. So here I cannot use Maclaurin series expansion for this, because if I write this in this way 1 over 1 minus z square, then also I cannot write in this, I cannot use Maclaurin series expansion of 1 over 1 minus z, because absolute value of minus z square is going to be absolute value of z whole square, that is greater than 1. So we cannot use this Maclaurin series expansion, we cannot use this series here, because absolute value of mod z square is greater than 1. So therefore we have to be careful, we are not considering our function in this way 1 over 1 plus z square. Instead of that we have to consider 1 by z square, because absolute value of 1 by z square is less than 1. So for that we can rewrite our function as this is as it is, and if we take z square outside this bracket, then we have 1 by z square plus 1. We are rewriting 1 plus z square as z square times 1 by z square plus 1. You can check by multiplying these two. If we multiply with z square, we have 1 plus z square, and because our z has absolute value bigger than 1, z will never be 0, so there is no problem in dividing with 1 by z square. Now we rewrite this as, we require powers of z, so we keep 1 by z into z square, that is z cube as it is, and we rewrite this as 1 minus 1 by z square. So now we can use that standard Maclaurin series expansion of 1 over 1 minus z. Instead of 1 over 1 minus z, we have 1 over 1 minus 1 by z square. So here we are considering nth power of minus 1 by z square, because 1 less than mod z less than infinity, therefore 1 is less than mod z. This implies absolute value of 1 by z is less than 1, and this implies absolute value of minus 1 by z square is also less than 1, and we are using the Maclaurin series expansion of 1 over 1 minus z. Maclaurin series expansion of 1 over 1 minus z, as we know, is nothing but sigma z raised to n equal to 0 to infinity, but this is valid if absolute value of z is less than 1. So if we want to use this Maclaurin series expansion, whatever we have in place of z, absolute value of that quantity must be less than 1. So here instead of z, if we compare these two, then instead of z we have minus 1 by z square. So we can use this series for minus 1 by z square if absolute value of minus 1 by z square is less than 1, and that is valid here because our z satisfies this inequality, absolute value of z greater than 1. So be careful whenever you want to use this series, you make sure that whatever quantity we have in place of z, absolute value of that quantity must be less than 1. Now this is simple, we can expand this, or first we rewrite this as sigma n equal to 0 to infinity. This we can rewrite as minus 1 raised to n divided by z raised to 2n. And now we can expand this. So we write one more step, 1 by z cube we keep as it is, or we can take 1 by z cube inside the summation, and then we expand sigma n equal to 0 to infinity minus 1 raised to n z raised to 2n plus 3. Now for n equal to 0 we have minus 1 raised to 0, that is 1 divided by z cube. For n equal to 1 we have negative sign, and this is z raised to 5. For n equal to 2 we have minus 1 square, that is 1, and z raised to 2 into 2, that is 4 plus 3 7, and then we can put n equal to 3, so 2 into 3 6 plus 3 9, and we have negative sign, and this is valid for those values of z which are in the domain 1 less than mod z less than infinity. So here we have obtained that all the powers of z are negative, and we can rewrite this as sigma n equal to 1 to infinity. In the denominator we have odd powers of z, that is z raised to 2n plus 1, and here we have to write minus 1 raised to n plus 1 because first term is positive. So if I take n equal to 1, I have minus 1 square. So this is the Lorentz series expansion of given function 1 by z times 1 plus z square, which is valid in the domain 1 less than mod z less than infinity. So in this way we can obtain Lorentz series expansion of this same function in different domains, and we have to be careful about the validity or convergence of the obtained series. So here we have seen that first series is valid in the open disk without center z equal to 0, and second series is valid for all points z which are outside the circle mod z equal to 1. So this is all about today's session. I hope you like this lecture, and in the upcoming lectures we will be doing this type of variety of problems on Lorentz series. Thank you very much.